In section 8.2, we're going to be dealing with multi-stage experiments and the multiplication principle of multiplying the probability of one event times the probability of another will be used most often. If you're asked to make a probability tree, this is what you will do. For example, if you want to know the probability of having 3 children where you have a girl, boy, boy in that particular order, we can set up a tree to help us count what could happen to get our outcomes. So for the first child, you could have a boy or a girl, and the probability would be 1/2 for a girl and 1/2 for a boy. Then for the second child, if the first child is a boy, the second child could be a girl or a boy. And the probability is 1/2 for the girl and 1/2 for the boy. If the first child is a girl, the probability would be 1/2 that the second child is a girl and 1/2 that the second child is a boy. Then the third child, if the first child is a boy, the second child a girl, then the third child could be a boy or a girl. If the first child is a boy and the second child a boy, the third child could be a boy or a girl. If the first child's a girl and the second child a girl, then the third child could be a girl or a boy. And then if the first child is a girl and the second child a boy, the third child could be a girl or a boy. So you read each branch and you write down the order. So you have a boy, girl, boy, and the probability is 1/2 times 1/2 times 1/2, which is 1/8. And then a boy, girl, girl. And again, that's 1/2 times 1/2 times 1/2, or 1/8. Then a boy, boy, boy. A boy, boy, girl. A girl, girl, girl. A girl, girl, boy. A girl, boy, girl. And a girl, boy, boy. So notice that the probabilities for each branch is 1/8. And if I add those all together, I get 8/8 or 1. Now, we were looking for a girl, boy, boy. So here is the only time that the girl, boy, boy in that particular order occurs. So one time out of 8, you would expect to get a girl, boy, boy ordering. Now, if you want just the probability of having 2 sons, then you would have 1, 2, 3 times out of 8 that occurred. Now, I didn't count this 3 because I said the probability of 2 boys. And so that the probability that you have all 3 boys would be different than the probability of 2 boys. So that's how you make a probability tree. Also, we now have to be careful that the events that we are dealing with are independent of each other. So we would assume then that the probability of having a boy or a girl would be independent for each birth. If you are spinning a spinner and flipping a coin, then we know that the probability of each would be independent of another. Now, where you run into situations where the probability would be dependent on another would be, let's say that you have a bag of marbles and you draw one marble out and you don't replace that marble. Then the second probability is dependent on what happened on the first. And so that's what we have to watch for when we're reading the problems, is that the probabilities will be independent for the 2 events. In this example, it says that a certain city's smog will be above acceptable levels 25% of the days, and its pollen will be above acceptable levels 20% of the days. So we're going to let S be the smog above acceptable levels, and we're going to let R be the pollen that is above acceptable levels. Now, first we have to decide whether we're dealing with independent or dependent events. And we have a formula that we can use that will help us to decide that. So if we first think of them as being independent, what is the probability the smog, pollen, or both will be above acceptable levels on any randomly selected day? So we're looking for the probability of smog plus the probability of pollen minus the probability that they will occur on overlapping days. So we're going to take the probability of smog is 25 hundredths. The probability of pollen is 20 hundredths. So you change those percents to decimals, minus the probability that they occur on the same day, the probability that they overlap. So when you do the math, so you're going to multiply first and then add and subtract, you get 40 hundredths, or 40% of the time you would expect to be above the level. So we added them and took away the days that they intersect, which multiplying them together does that. Now, the next part of this says, suppose records actually show the probability of a day occurring with both smog and pollen above acceptable levels is 8 hundredths. So we have some data about this overlapping section that we just predicted. Now, the test for independence is if you look at this intersection, which we found by multiplying the two together. When we multiply 25 hundredths times 2 tenths, we end up with 5%, or 5 hundredths. So when you actually multiply them together, you get 5 hundredths. But the data that we are given in this table says that the overlapping days are actually 8 hundredths. So these two are not equal. The data that's given is not equal to what we calculated. Therefore, these are dependent events. So if the data given doesn't match the product, then they are dependent. So now when we work the problem, and it says, what is the probability the smog, pollen, or both will be above acceptable levels on any randomly selected day, we use the data that was given later in the problem instead of what we calculated. So we now, in the third part of the problem, we'll still use the same formula, but we will use the information that was given to us about what is predicted to be the number of overlapping days. So we would have 25 hundredths plus 20 hundredths minus 8 hundredths. So this would be the probability, and we get about 37% of the time that would occur. So again, we can determine whether events are dependent or not by taking the intersection values compared to what would be given to you in the problem, the data level that was part of the problem. That would need to be given to you. It would not be something that you would just automatically know. Another term, complementary events. If I know that the probability of spinning a spinner and getting red is 1/4, then I know that the probability of not getting red, which is the complement, not red, would be 1 minus 1/4. So in some problems, it is easier to find the probability of the event occurring. And then if it wants the probability that it did not occur, you simply take the probability that it did away from 1. So that's what a complement is. In gaming, we want to know what is our expected value. So if I play this game enough times, what will overall be expected to happen? Because, often we can be lucky and win, but also often we can lose. More often we will lose than win in gaming. That's why, casinos can stay in business, because the probability of you winning is less than the probability of you losing. But let's say that we are playing a game. We are rolling 2 dice. And if the player obtains a sum of 7, she or he is paid $5. Otherwise, the player pays $1. So over time, can the player expect to gain money, lose money, or break even? So if we think about that for a minute, in our past section, we had the table showing all the sums that we could get when we rolled 2 dice. And we found that if we have a 1-6, a 2-5, a 3-4, a 4-3, a 5-2, and a 6-1, then we're going to get a sum of 7. We also remember from the chart that there are 36 combinations, and there are 6 successful. So the probability is 1/6 that you would get a sum of 7. So 1 out of 6 times you play this game, you're going to get $5. So we will set that up. The probability of getting a 7 times $5 that you will get paid. And then you're going to pay $1. So that means that you're going to lose $1. And if the probability of winning is 1/6, then the probability of losing is 5/6. So this is the probability of winning. This is the probability of losing. So 5 out of 6 times I'm going to play this game, I'm going to pay $1 and lose it. So when I multiply these together, I get 0, which means that if I play this game over a long period of time, I'm going to just break even. That means that this is a fair game. When you just break even, then you know that it's a fair game. All right, another example like that. We have a sweepstakes ticket, and it has hidden dollar amounts that might be $50, $20, $5, or $1. And if you have 3 identical dollar amounts, then you win that amount. So there's also a $10 bonus amount on the ticket if a sun symbol is revealed. So the probabilities of winning $50 is 1 over 500. The probability of winning $20 is 1 over 200. $5 is 1 over 500. $1 is 1 over 10. And the $10 is 1 over 200, respectively. Now, anytime you get a sweepstakes letter in the mail, if you look at the little teeny weeny tiny print on the very bottom of the very last page, it will give you the probability of winning any of the particular prizes that they have. So in the first question, it asks, what are the expected earnings? So to get the expected earnings, what you will do is multiply the amount times the probability. So $50 times the probability of winning $50 plus $20 times the probability of winning $20 plus $5 times the probability of winning $5 plus $1 times the probability of winning $1 plus the $10 bonus times the probability of winning the $10 bonus. So this means that 1 out of 200 players will get $10. 1 out of 10 players will get $1. 1 out of 50 players will get $5, and so on. So I'm going to multiply these together, then add them. And your expected earnings would be 45 cents. So if you played this game over a long period of time, your expected earnings would be only 45 cents. Well, you had to pay to play the game. So whatever you paid would be minus this amount. So let's say it cost you $1 to play. That means that you, in the long run, would be 55 cents in the hole. So this is your earnings, but it did not take into account what you paid to play the game. Once you get your earnings, you take it away from what you had to pay to play. So if you had to pay $5 to play, then you're going to take your earnings minus what you had to pay to play. And anyway, you're going to be in the hole in this game. Now what that means is this is not considered to be a fair game. Because a fair game, you would end up with 0 as earnings over a long period of time. A permutation is an arrangement of objects in a particular order, like president, vice president, secretary, first place, second place, third place, blue ribbon, red ribbon, yellow ribbon. There is an ordering, a particular order to the problem. Now, n factorial means that you're going to take the number and you're going to multiply it down to 1. That's what n factorial means. So when we work with permutation problems, we have to use a formula that has factorial in it. For example, how many different ways are there to place 3 different colored tiles in a row of first, second, and third? Well, in this problem, it's pretty easy because we could draw our first, second, and third place. And if we have 5, now there's 3 different colored tiles. So the first place, there are 3 ways that we could fill the first place position. But once someone fills the first place, there's only 2 people left that could be second. And once second place is filled, there's only 1 person left that could be third. So if we multiply these together, there would be 6 different combinations of first, second, and third out of 3 people, or 3 colors. So the formula that we use for permutations is written like this. We use n to represent the number of objects, like we had 3 colored tiles, and r represent the number of them that we're going to use. So we had first, second, and third, so we were using 3. And that's going to be n factorial over, in parentheses, n minus r. So you have to subtract them before you do the factorial. So let's say that we are looking at a basketball team, and I have 20 boys that are trying out for the team, and I'm only going to choose 5 of them to play today. So the n on the problem would be 20, and the r on the problem would be 5. So I have 20 boys, and I'm going to choose them 5 at a time. How many different how many different ways can I position them as first, second, third, fourth, and fifth? So I want to position them in this order: first, second, third, fourth, fifth, because in permutation there has to be an ordering. Now, the wording of the problem will tell you if there is an ordering. It will not say solve this permutation. So you have to read it and decide if there is order to the problem. So I'm going to take these 5 boys that I choose out of 20, and I'm going to place them in first, second, third, fourth, and fifth. So the formula, n, which is 20, r, which is 5, is equal to 20 factorial over 20 minus 5 factorial. So 20 boys positioned 5 positions would be 20 factorial over 15 factorial. Now, if I begin to count backwards with 20 until I get to 15 factorial, the 15 factorial will cancel out. So I have 20 times 19 times 18 times 17 times 16 times 15 factorial over 15 factorial. So that goes out. So now all I have to do is multiply 20 times 19 times 18 times 17 times 16. Now most calculators have factorial or permutation keys on them. And so you can look at yours and it will be an NPR is what it will look like on your calculator. We also have the combination. And the combination does not consider order at all. If you just want to take 20 students and take them out 5 at a time without considering first, second, third, fourth, fifth place, then you're dealing with a combination. So order is not important. And again, in the wording of the problem, it will not say find the combination. You have to judge whether you're positioning them by order to get a permutation or you're positioning them as a group where order is not considered. So how many different collections of 3 tiles can be chosen from a set of 5 different colored tiles: red, blue, green, yellow, and orange? So we are going to be looking at a combination because order is not important. And the formula for combinations also deals with factorial, but it's written a little bit different. You take n items, r at a time. You have n factorial over n minus r factorial times r factorial. So it's a little bit different than the permutation. So let's look at this example where n is 5 because there are 5 tiles. R is 3 because you're taking them 3 at a time. So we will use our formula. 5 items taken 3 at a time is 5 factorial over 5 minus 3 factorial times 3 factorial. Now again, you can use your calculator. It'll have an NCR key on it, but these sometimes are pretty simple to do by hand. So I have 5 factorial over 5 minus 3 is 2 factorial times 3 factorial. Now you can't multiply the factorials together, but we can write them out. So I have 5 times 4 times 3 factorial. So I'm going to stop there because the 3 factorial cancels out. So if I continue to solve, I have 5 times 4 on the numerator. 2 factorial in the denominator is just 2 times 1. So the 2 into 4 goes 2 times, and 5 items taken 3 at a time would have 10 different ways of writing them.